All right, let's get straight to it. Today, we are going to absolutely conquer the trickiest part of the AS Physics Paper 3, that big 6-mark evaluation question. We're going to break it down into a super clear tactical guide so you can walk into that exam feeling totally in control.
This is the question, right? It's where so many people drop marks. But trust me, by the end of this, you'll have a solid strategy to spot limitations, come up with powerful improvements, and nail every single one of those points.
And let's not forget what's at stake here. 6 marks, just for this one part of one question. That can easily be the difference between a grade A and a grade B. Getting this right is absolutely crucial. So what even is question 2? Well, think of it as an error analysis task. The examiners have literally handed you a method that they know is full of flaws. Your job is to step in like a real scientist, spot those weaknesses, and propose smart, specific solutions. Vague ideas just aren't going to fly here.
Okay, let's kick things off with an easy win. I'm talking about one point that is so common, it's pretty much a guaranteed first mark. Think of this as the foundation for your whole answer.
And here it is. This is your golden ticket. The limitation is simple. 2 sets of readings are not enough to draw a valid conclusion. And the improvement? Just as straightforward. Take more readings and plot a graph. Seriously, this works for almost every experiment they can throw at you.
And here's a crucial tip straight from the examiners themselves. It's not enough to just say, take more readings. You must mention plotting a graph. And why is that? Because a graph is how you see the trend, how you spot any weird outliers, and how you actually prove a relationship exists. That's the real physics.
All right, you've got that first mark in your pocket. Now let's build the rest of your toolkit. We're going to go through the 6 most common types of errors you'll find. If you can learn to spot these, you're pretty much unstoppable.
First up, timing things that move fast. The limitation is not human error. That's a classic answer that gets 0 marks. The language you need is, it's difficult to judge the start and end of the movement because it's too fast. The improvement has to be a technical one. Say something like, use a video camera with a slow motion feature and a timer in the frame. That lets you do frame-by-frame analysis, which is a huge leap in precision. Next, let's talk parallax. It's not good enough to just write down parallax error. You got to say where it's happening. For instance, parallax error when measuring the height h because the ruler isn't sitting flush with the object. And the fix needs to be better than just view it at eye level. Suggest a proper technique, like using a mirror scale or grabbing a set square to make sure that ruler is perfectly upright. Things in the real world are rarely perfect. A wire might be thicker in some places, or a ball might not be a perfect sphere. So the limitation is that the object isn't uniform. The proper scientific procedure, and the one that gets you the marks, is to measure the diameter at several different points and in different orientations, and then calculate a mean.
What about when the whole setup is just wobbly, or things keep slipping around? Again, writing "be more careful" is a waste of ink. The limitation is that the apparatus is unstable. The improvement is a simple, practical fix. Say, clamp the stand to the bench, or use a bit of adhesive putty to secure the mass hanger. These are real, concrete actions.
Sometimes the room itself messes with your experiment. For light things, like a pendulum, the issue is that it's affected by wind or drafts. The solution isn't just turn off the fan. The more scientific answer is to use a windshield. And if you're working with water and can't see the surface because of a meniscus or refraction, the easy fix is to just use a colored dye.
Okay, now this one is really clever. The problem is that measuring something tiny leads to a huge percentage uncertainty. The obvious answer is use a more precise instrument, but that often gets rejected. The smarter move is to change the experiment to make the thing you're measuring bigger. So instead of timing one swing of a pendulum, time 20 and divide by 20. This massively shrinks your percentage uncertainty.
Okay, so you've pointed out all the errors and suggested great improvements. Now for the final part of the question, the math. You'll often be asked to check if your results actually support a given relationship. Let's lock in those last couple of marks.
It's a simple 3-step recipe. It works every time. First, calculate the percentage difference between your 2 values for the constant k. Second, compare that difference to a sensible percentage that you choose, maybe 10% or 20%. And third, write a nice, clear conclusion that connects those 2 things.
And honestly, you can pretty much just memorize this sentence. It leaves absolutely no doubt. Since my percentage difference of, say, 8% is less than my 10% criterion, the suggested relationship is supported. If it's bigger, you just say it's not supported. It's that simple. That explicit comparison is what they're looking for.
Woof, we've covered a lot.
So let's boil it all down into a final rapid-fire checklist of what you absolutely should do, and maybe more importantly, what you should never, ever do.
Okay, on the left, the do's. Always be specific to the experiment in front of you. Suggest technical upgrades like video analysis or fiducial markers. Use precise scientific language. And on the right, the don'ts. I'm begging you, never write human error or reaction time. Never suggest getting a friend to help. And don't be vague. Saying something was hard to measure gets you 0 marks. You have to explain why it was hard.
And for a final little memory boost, try to remember these. For the limitations, think timing, stability, parallax, small measurements, uniformity, fluids, and wind. That's T.S.P.S.U.F.W. For the improvements, graph, video, mean, adhesive, larger measurements, and shield. That's GVMALS. Run through that list in your head during the exam, and I promise you'll spot the key issues.
So there you have it, a complete game plan for what used to be the hardest question on the paper. You see, the examiners are giving you a broken experiment. They're basically inviting you to show them what a great physicist you are. This question isn't a trap, it's an opportunity. So are you ready to turn their errors into your advantage? You've got this. Good luck.